Welcome back, everyone. So we'll sort of continue from where we had left off yesterday. So just to recall, we had introduced our main examples: Z2 synchronization, community detection for the block model, and sort of community detection with contexts. And we saw what the main statistical questions were in this context. So detection, recovery, and sort of optimal recovery. And then we saw some lower bound ideas. Right. So we saw some ideas on how to derive information theoretic lower bounds for these problems. Our goal today is to kind of look at the positive side of the problem, or the so-called upper bounds. So we'll come up with, we'll discuss very specific algorithms for detection and recovery, okay, in these specific problems. And I mainly plan to talk about two classes of algorithms. One are so-called spectral algorithms that are based on doing the spectral decomposition of some matrix constructed from the data, and some convex relaxation based methods based on semidefinite programming. Okay. So that's essentially my goal for today. But maybe before I jump into this, let me pause to see if there are any questions from what we did yesterday. Anything? Make sense? Okay. Okay, so let's jump into spectral algorithms. And let's start with sort of our simplest example, Z2 synchronization, right? So recall what this problem was. I had some vector sigma that was uniformly sampled on the n-dimensional hypercube, and then I observed a matrix which is lambda over n sigma sigma transpose plus additive Gaussian noise, right? This was what I have seen, and our goal for now is to actually construct a vector sigma hat that has non-trivial correlation with sigma, right? That's what I want to do. So goal is construct an estimate sigma hat, which is sigma hat of m basically. So a function of the data such that if I look at the inner product between sigma and sigma hat, so this is sort of the correlation, I want it to be bigger than epsilon. So this probability I want to go to 1, right? Okay, so how should we go about constructing such an estimator? So here is a sort of first level idea, right? The point is to note that because this is centered Gaussian noise, if you look at the expectation of m given sigma, that's exactly lambda over n sigma sigma transpose, right? That's fine. So therefore, generally, I can decompose my matrix as the conditional expectation plus some kind of an error term. Right? And the point is, instead of the matrix M, if someone only gave you this conditional expectation, this would be a rank 1 matrix, right? So if you did like a spectral decomposition of this, you would immediately recover sigma. Okay? And so therefore, the natural idea here is to say, okay, I have this matrix M. It's basically like some signal component that I really like and I would like to know. And then there is some additional noise component, right? So if the noise component is not too large, then maybe if I do spectral decomposition on this corrupt object itself, maybe I will already discover something that will have some non-trivial correlation with the signal that I care about. Does that make sense intuitively? Right. So this suggests the following algorithm. It's a naive spectral algorithm, right? Basically has one step. Take the top eigenvector of M as an estimate for sigma. And of course, you scale this appropriately. When I talk about the top eigenvector, what I am referring to is the eigenvector that has been scaled to have norm root n. Right?
And then the coordinate by sign, or what do you mean?
So here, because I just wanted to have some non-trivial correlation, I don't necessarily require that the entries of sigma hat are plus or minus 1. But if I want that, I can also round things appropriately. Okay. Okay, and turns out, at least in this setting, even this simple spectral decomposition based algorithm works. And so this is a theorem. This has actually very long roots in random matrices. So let me just state the theorem. So it comes in two parts. First part essentially is that if lambda is less than equals 1, so remember that lambda equals 1 is the information theoretic threshold for the problem, so nothing can work, and so in particular you don't expect the spectral algorithm to give you anything meaningful here. So in this entire regime, if you look at the largest eigenvalue of the matrix M, then this converges to 2 almost surely. And then if you look at the normalized correlation, and if V hat PCA is the top eigenvector, let's say with unit norm, then 1 over n sigma V hat PCA squared goes to 0. That's what happens below the information theoretic threshold. And if lambda is bigger than 1, then lambda max of M actually converges to lambda plus 1 on lambda almost surely. And if I look at 1 over n sigma V hat PCA squared converges to 1 minus 1 over lambda squared almost surely. Okay. Okay, so let's parse this statement for a bit, right? So there are two cases. One case is, what happens for lambda less than equals 1. Actually, what happens is that if you look at this matrix M, and if you look at its entire spectral distribution, so the empirical distribution of the eigenvalues, then it converges to this so-called semicircle distribution, right? And the top and the largest eigenvalue essentially sticks to the edge here, right? And if you look at the corresponding top eigenvector, it doesn't have any correlation with the planted truth, right? And therefore, as you expect, if you try to detect the presence of the signal based on just the value of the top eigenvalue, based on the top eigenvalue, it doesn't have any power. In fact, no test has power. The test based on the largest eigenvalue also doesn't do anything non-trivial. Yeah.
So the semicircle thing is for a Gaussian random matrix, right?
Yeah, but the matrix M is like a one-rank perturbation of a Gaussian matrix, so it doesn't change the bulk spectrum. So it doesn't change anything but one of the eigenvalues. So here, yeah. So even when lambda is bigger than 1, if you look at the empirical distribution, that will stay the same. Right, so that's what I'm coming to next. So in the regime of interest, if you go to lambda bigger than 1, if you look at the empirical distribution of eigenvalues, it's still the same. It kind of looks like this. But now there is an outlying eigenvalue somewhere here. And this is at lambda plus 1 on lambda. Right. And now if you take the corresponding eigenvector, and if you look at its correlation with the truth, then there is something non-trivial that happens. Okay. Any questions on this?
So is there an intuition why the lambda guy in case A is below 2? So the Gaussian matrix has random. So this is putting some energy in this direction, right?
Right.
Why is that not being pushed out of this semicircle somehow?
Right. So it is being pushed once that direction is strong enough. Right. So the point is, if lambda is very small, for example, if lambda is close enough to 0, then you don't expect the energy that you put in the direction 1 to be enough to push the eigenvalue beyond the 2 threshold. Turns out that this transition effectively actually happens at lambda equals 1. What is actually surprising here, and I think Shiva's question also kind of carries this, is that naively, if you are encountering this phenomenon for the first time, you would imagine that this outlying eigenvalue could be created if you put a lot of mass in the direction sigma, right? And if the outlying eigenvalue were being created simply by the mass that you put along the direction sigma, you will see, if you do some back of the envelope calculations, that you will need lambda to be much bigger. Actually, if the outlying eigenvalue were being created just by the mass here, you would need lambda to be equal to 2. But the interesting thing that happens for this particular problem is that there is some repelling effect among the eigenvalues, and in fact the outlier is pushed out even for a much smaller value of lambda. Okay, so that there is something interesting that is going on here. Yeah.
Also, are you using the sigma as uniformly random as well, or does it work also for a fixed sigma?
So if the noise is actually Gaussian, then it doesn't really matter, right? Because everything is rotationally invariant, I can put in an additional rotation. But this theorem itself, it holds for other kinds of noise models and things like that. You don't really need a Gaussian model on the noise as long as the noise is sufficiently light tails, and so we know a lot more there, and then we might need to assume a bit more on the spike. Okay. Yeah.
If you have a finite sigma, it's the same result holds.
Sorry, when you say fine.
If you have two sigma.
Oh yeah. So instead of like a rank 1 perturbation, if you have like a rank k perturbation, then we also have a very clear understanding of when there are one outlier eigenvalues, 2 eigenvalues, and so on and so forth, what their relative locations will be, and so on and so forth. Right. So yeah, I present this in the context of a rank 1 spike model, but this is known in much more generality. Yeah.
Can you say more about the 1 to 2 thing? You said some repelling is happening.
Yeah. So so the thing that is known is that, for example, in the case of, if you didn't have this spike. If you just had the pure noise model, and if this were Gaussians, then in this very special case, you can write down the joint distribution of all the eigenvalues. And so those, for example, form a point process, right, all the eigenvalues. And if you look at that joint distribution, it's kind of clear that the eigenvalues don't tend to bunch up too much. So they actually push each other apart. That sort of comes from the exact form of their joint distribution. And the intuition, okay, so what I'm saying is a bit more of an intuition, but it's sort of this thing that because these eigenvalues tend to push them apart, when you have one of these eigenvalues at the very edge, it feels the push from everything else in the bulk, and therefore gets pushed out at some point. Okay. So this is the result. Okay, so what is the algorithmic takeaway from this? The algorithmic takeaway is very simple, right? The algorithmic takeaway is that to perform consistent detection or weak recovery for any lambda bigger than 1 can use the top eigenvalue or eigenvector, right? And now you can see, coupled with our discussion from yesterday, that the information theoretic threshold for detection and weak recovery in this problem is exactly lambda equals 1. I mean, we saw the lower bounds for detection. There are similar arguments proving that below lambda equals 1, you cannot also recover using any algorithm, not just the spectral one. Okay. Any questions? Okay, so this is really nice. And at this point you might say, well, if I once I have these results, I can be, when I'm designing algorithms, I can be sort of really ambitious, and I can say whenever the hidden signal in my problem sort of has this low rank structure, I can just take whatever matrix I have, I can apply some SVD or eigenvalue decomposition, work with the top eigenvectors. Maybe they always work well, right? Maybe this is kind of an all-purpose algorithm that can always give me useful results. Okay. So I'll refer to this algorithm, this entire scheme, as the naive spectral algorithm. And therefore, here is a question for us. Does the naive spectral algorithm always work? Right? Okay, so let's see what happens in the context of a very related problem, right? Let's look at its behavior in the context of community detection. And so recall again that for community detection, I have kind of a similar structure, right? I have sigma i's that are IID plus or minus 1. These are my community assignments, and then probability that ij is an edge. This is A over n if sigma I is equal to sigma j, and is B over n otherwise, right? And A and B are fixed constants independent of n, right? This was our model. And if you remember, in our last discussion, I was kind of drawing some parallels between the community detection problem and Z2 synchronization, right? So in particular, if A is the adjacency matrix of the graph, then, and if I set the parameter D to be A plus B on 2, then if I look at A minus D over n 1 1 transpose, the vector 1 is, a vector of length n with all entries being equal to 1, and this is therefore the constant matrix. I can write this as the expectation of A given sigma minus D over n 1 1 transpose plus A minus expectation A. So I haven't really done anything. This is just algebra. I have decomposed this term into a sum of two terms. Now, naturally, if you follow our heuristics from the discussion in the context of Z2 synchronization, you'll say, okay, this is kind of mean zero noise, right? Okay, how does this matrix look? So if you look at the matrix A, roughly, if you reorganize the elements so that the first half are in the first group and the second half are in the second group, then roughly the matrix, this is how it looks, right? So if the first half entries are +1 and the second half are -1, then it has this block structure. So this implies that if you look at expectation of A given sigma minus D over n 1 1 transpose, this has exactly this structure, A minus B on 2n times sigma sigma transpose. And therefore now, okay, so once you put this to be equal to, now you have the same kind of insight, right? You would feel, okay, I look at this matrix, when I see the graph, I obviously have the adjacency matrix given to me. We assume throughout that the parameters A and B are known, so D is known. I can subtract off this thing and construct this matrix. This is something I can construct. I know that this is basically a rank 1 matrix plus some noise. So if the noise is small, maybe I can just apply the same spectral decomposition based algorithm, and I should recover something based on sigma, right? It's exactly parallel to our earlier discussion. Okay. Unfortunately, this naive spectral algorithm does not work in the context of community detection, at least in this sparsity regime. So fact is that naive spectral algorithm fails for community detection. At sparsity 1 over n, and this is important. So in this regime where we have restricted ourselves, where the edge probabilities are of order 1 over n, in fact, if you look at just the top eigenvalue and the eigenvector for the top eigenvalue, these will not give you any useful information regarding the underlying community structure. Okay. Why is this the case? Yeah.
Oh, that's exactly what I was thinking.
Right. So I'm coming to that. Why is this the case? What is really happening? Okay. So to kind of demystify this a bit, let me take a step back. And instead of talking about graphs drawn from, a stochastic block model where there is an additional community structure and all, instead of talking about this, let me first talk about even the Erdős-Renyi graph, right? So simpler object. But there are things that happen here that are kind of universal for all these random graphs that are essentially going to stop the spectral algorithm from having a positive behavior. But let's look at even sparse Erdős-Renyi graphs for a moment. So sparse Erdős-Renyi random graphs. So this is actually a very famous result due to Krivulevich and Sudakov. From 2001. Now suppose G is an Erdős-Renyi graph with n vertices and edge probability p, right? So I have n vertices, edges are added independently with probability p. P can depend on n, but I'll keep that dependence implicit. And suppose A is the adjacency matrix. Then lambda max of A, this is the largest eigenvalue, essentially behaves divided by the max square root delta and np. This goes in probability to 1, right? Where delta is the max degree. Okay. So the result of Krivulevich and Sudakov essentially says that if you look at the adjacency matrix even of an Erdős-Renyi graph, and if you look at its maximum eigenvalue, it's essentially governed by the maximum of two things. It's either np, which is the expected degree in your graph, or by the maximum degree, or square root the maximum degree. Okay? And what is true now is that if you are in the sparse regime, so if p is like a constant over n, then of course your np is an order 1 object, that's fine. But if you look at your maximum degree, this is much larger, right? Because each degree effectively is like an independent Poisson or an independent binomial, roughly, right? And you're looking at the maximum of n of them. So the maximum degree actually is of order log n over log n. And therefore, this actually implies that lambda max of A is actually of order square root log n over log n in this regime. Okay? Okay, so now, okay, at this point you might say, what does this have to do with the failure of the spectral algorithm for community detection, right? What is the connection? So turns out that, if you look really, if you squint at their proof of Krivulevich and Sudakov, not only do they characterize the behavior of the top eigenvalue, they actually explain why the top eigenvalue essentially behaves in this way, right? So what they say essentially is that if you have this kind of sparse random graph, if you look at its adjacency matrix, it can have an eigenvector that essentially puts most of its mass on a vertex with very high degree. This leads to the creation of this large eigenvalue that roughly has, value which is square root the maximum degree, right? And okay, so in your graph you have some vertices that have degrees that can be as large as log n over log log n. Therefore, you can have now these eigenvectors that put most of its mass on these degrees, or on these vertices of high degree, and this leads to sort of these outlying eigenvalues in the adjacency matrix. Now, a similar phenomenon essentially happens in the context of the stochastic block model, right? Because all your edge probabilities are of order 1 over n, you still have these vertices of large degree, and you still have these outlying eigenvalues that can be as large as square root log n over log log n. And therefore, now you can understand that if you just naively take the adjacency matrix and look at its largest eigenvalue, that is essentially just coming from this vertex of large degree. That has nothing to do with the underlying community structure, right? So if you take this eigenvector, if you round it or try to project it down to something, it will give you pure noise. You will not recover any signal. Okay. Does this make sense? Yeah.
So essentially, the fundamental issue is that the eigenvalue behavior is very different in these two settings. So
right.
Essentially, if I have a matrix and I sample all the entries by Gaussian, we have that behavior.
Right.
If I sample all the entries by Bernoulli, we have this behavior.
Yeah.
So is there like a way of thinking about why this Gaussian versus Bernoulli gives such drastic difference?
It's a matter of the tails, right, of the entries. It's a matter of the fact that if I look at the row sums, essentially, of the adjacency matrix, then in the Gaussian case, they are still Gaussian, so they have Gaussian-ish tails. If I look at the sums, they are in the adjacency matrix of a sparse graph, they are binomials or Poissons, so the tails are much heavier. And that leads to things to blow up.
Okay.
So it's essentially a matter of somehow the tails actually having a role to play.
Okay. Cool. Thanks.
Okay.
Oh, then as a follow-up, so if I do a continuous distribution instead of Gaussian, I do something like exponential or something like that, then would we expect more of this kind of behavior?
Right. Okay. So a lot is known about this. I don't know right at the top of my head, but for example, people have explored this entire phenomenon in the context that, okay, instead of having Gaussian things, if I have things with, let's say, 4 or 5 finite moments and all of these things, when are these things true? In some cases, they are true. If I don't have enough moments of the entries, then some cases they fail and you have outliers, things like that.
Thanks.
Okay, so the question essentially at this point is, what do you do? Question is, what should one do? And there are a few different options. And people have actually explored all of these options. You can say, well, this result essentially tells me what is going wrong in this particular case, right? You have these vertices of very high degree that anyway aren't giving me any useful information, and they are actually like interfering with the behavior of the spectrum. So I can just take my graph, I can prune away vertices of large degree, and then I can work with the rest of it, right? So one idea would be, I don't want to change my algorithm too much. I can just prune the vertices of large degree. Right? That's one idea. A second idea is, okay, I want to stick with spectral algorithms, but I don't need to use the adjacency matrix itself, right? Like I can construct other matrices and maybe do, you know, spectral decompositions based on the new matrices I obtain. So I can use potentially alternative spectral methods. That's a second fix potentially. And then a third fix is to say, fine, spectral algorithms can have sort of strange behaviors. Maybe I give up on spectral algorithms altogether and look at other classes of methods. So alternative algorithms less sensitive to high degree vertices. Right. So these are all, you know, options. And in fact, people have explored all of these options. And I plan to talk about all of them at different degrees of depth, okay, today. Okay, so let's see. Okay. So first, to kind of see what we can do to fix the issue here, let's recall the actual information theoretic threshold, right? Let's recall that in this community detection problem, I set D to be A plus B on 2, and I set a parameter lambda to be A minus B on square root 2 A plus B, right? And the result that we quoted from last time is that detection and weak recovery works if and only if lambda is bigger than 1. Right? And throughout, I assume, you know, it's implicit that D is bigger than 1. This was our result from last time, right? And we are trying to establish a positive part of the result. So we have to come up with an algorithm that does the detection and can perform weak recovery as soon as lambda is bigger than 1. Okay, so formally, if you try the first approach, which is pruning, there are actually results that, you know, if you take the graph drawn from the stochastic block model, if you prune appropriately, then you can prove at least that you can make spectral algorithms work for lambda actually bigger than some large constant C naught. Okay? So if lambda is very large, you can prove that even pruning works. It gives you weak recovery. Okay? But I mean, in practice, I think it's a good strategy. It's a practical strategy, right? But from a purely theoretical perspective, I think it has been difficult to get this threshold down to the conjectured threshold of 1 with the pruning-based method. So the second approach, which is based on, you know, finding alternative spectral algorithms, actually has been much more successful. So I'll talk about spectral algorithms based on the so-called non-backtracking matrix. So this method was actually conjectured using non-rigorous tools from statistical physics around 2011, 2012. There were, very conclusive simulations, and so proving this result for a while was sort of, something that was really of interest, and this is now known formally. So let me describe the result. So this is a new class of spectral algorithms. So you say, okay, you give me the graph. Based on that graph, I will construct some other matrix, not the adjacency matrix. And then I'll apply the same algorithm. I'll still do eigenvalue decomposition and then work with the eigenvector corresponding to the top eigenvalue. That's what I'll do. But I will work based on a different matrix, right? The so-called non-backtracking matrix. So what is this? So I give you a graph G with vertex set V and edge set E. And this is undirected, right, generally, so far for us. So what we do is that first, if ij is an edge, then we add two oriented edges, E, which is the edge ij, and E inverse, which is ji. Okay? So you give me your undirected graph. I take this graph, now I construct a directed graph, where for each edge in my original graph, I add both the directed edges. Okay? And now I will construct a matrix B, which is actually indexed by the directed edges. So it has size 2 times the number of undirected edges. That's the size of this matrix. It's a square matrix. And the entries are indexed by the directed edges, right? So if I give you 2 directed edges, E and F, then this is indicator that E2 is F1 and indicator that E1 is not F2, where these subscripts essentially indicate the 2 endpoints of the directed edges. Okay, let me parse this construction a bit more. So you have now these directed edges, right? So if I have 2 directed edges that essentially look like this, right? So this is E and this is F. So the end point of E is the starting point of F, and it doesn't go back. So if this is the configuration, then I add a 1 corresponding to this matrix entry. Otherwise, every entry is 0. This is my matrix. Now, there is one thing here that I should point out, which is a bit different from what we have been doing so far. This matrix generally is not symmetric. And therefore, it can have complex eigenvalues as well. But this is an n by n matrix, generally not symmetric. I can construct this if you give me the graph. Okay. So what is the result here? The result and this is due to Bordunov Lelarge and Massoulier, around 2015, and I'll just state an informal version of this. So the spectral algorithm based on B, sorry, performs detection and weak recovery as soon as lambda is bigger than 1. So lambda, recall, is this parameter. Okay. So this is one algorithm that achieves the information theoretic threshold for detection and recovery, right? So what happens is that there are two cases. If lambda is less than 1, I think even less than equal to 1, if you look at this matrix, all its eigenvalues are contained in a ball of a certain radius on the complex plane. You have these pictures, you know, everything is contained here. Whereas if lambda is bigger than 1, then if you look at the eigenvalues, everything else kind of looks the same, but there is one outlying real eigenvalue. And if you take the eigenvector corresponding to this real eigenvalue and if you round it, that will give you weak recovery. Okay. So that's the result. This is a very deep result in this area. And it attracted a lot of attention, and sort of lots of new tools were developed to prove this. But sort of at a high level, taking a step back, it's kind of pointing to the success of this second approach, where you say, okay, I will still do spectral decomposition based algorithms, but instead of working with, you know, the first matrix I can think of, I might need to re-engineer the matrix that I work with. Right? And for a moment, if you think about it, you might be like, okay, why should I even think of this non-backtracking based matrix, right? How did I come up with this? Why does this work? So if you think about this, you know, we realized that the main barrier for the naive spectral algorithm was the existence of vertices with very high degrees, right? That's sort of what was kind of making things worse. Now what will happen here is that because you are not looking, you know, you're looking at the non-backtracking matrix, imagine this vertex, right? If this were a vertex of very high degree, it has many edges that pass through it, right? So essentially, the fact that I'm doing sort of this non-backtracking operation helps me rule out these walks of small length that essentially go from a certain vertex directly to a vertex of very high degree and immediately come back. So essentially, I'm ruling out those paths. And therefore, this non-backtracking based method is essentially, you know, kind of damping out the effect of vertices of very high degree. That's kind of the intuition as to why you might expect this to work. But it's still not, you know, obvious or immediate in any way. But a posteriori, you can kind of squint at it and sort of form this heuristic and intuition for the success of this method. Okay, let me pause here for a bit. Any questions so far?
So this going and coming back heuristic that you explained, how does that relate to the eigenvector?
Right. Okay. So what I was kind of referring to is, I think, more of what happens to the eigenvalue, right? In the sense that, so I was kind of talking about this thing. Roughly, let's say if I have the adjacency matrix, right? Let's say A is my adjacency matrix. if I want to look at the lambda max of A, one thing, this is approximately the trace of A to the L raised to the 1 over L, right, for L large. Maybe like logarithmically large or something. And then if you look at the trace of this is essentially, sum of all closed walks on the graph. Of length L. And so what is happening is that if you now have these vertices of very high degree, essentially when you look at your walks, the walk gets dominated completely by things coming, passing through these vertices of high degree. That's why you essentially end up creating these outlying eigenvalues. But instead now if you look at the top eigenvalue for the non-backtracking matrix, you don't allow these things to kind of repeatedly jump back and forth. So you're explicitly ruling out this thing. So turns out, I should make a comment here, and I'll come back to it sort of in the second part of the talk today. It turns out that there are many different ways to kind of damp out the effect. Like here I mentioned non-backtracking walks. It is also known, and I'll talk about this more, that you can as well work with self-avoiding walks. They do the same thing. They kind of rule out the effect of high degree vertices, but it's just that algorithmically this is much more easy to implement. Counting self-avoiding walks is still not a very efficient strategy. Okay? But the entire point here is to come up with many different ways in which you can explicitly identify the main barrier and rule them out. Yeah.
I'm confused because for A is a matrix on vertices, but this B is a matrix on edges.
Right.
So like this interpretation is very nice. Is there a similar interpretation for B in terms of walks and stuff like that?
If you definitely, yeah, so it's not directly in terms of the graph anymore, but like if you count, okay, what is going on with trace of B to the L, then you'll basically see what are paths between edges now that essentially go through. So it's a slightly more indirect connection there. Yeah. Okay, so I think I'll pause here for the time being, and then for the next part of the lecture today, we'll talk about a different class of algorithms based on convex relaxations and semidefinite programming. What did we see so far? So we've seen that, okay, there are settings depending on the model where even naive spectral algorithms can be great and they can work well and help you achieve the information theoretic threshold. There are settings where the naive spectral algorithm itself, might not work well, but with some careful design choices, you can come up with other matrices where you can apply the same spectral heuristic and it will still work well. And now you can say, okay, fine, at this point maybe I want to do something different. Maybe I want to see if there are other algorithms out there that anyway conceptually kind of, address this problem of high degree nodes without having to, think carefully about specific model-based characteristics, right? So to that end, I want to talk about sort of some convex relaxation-based approaches based mainly on semidefinite programming, right? And so I feel that there have been a few different strategies that have, come up in terms of how you should get this, how you should construct such a semidefinite program and what you can prove about it. So I plan to talk about two different approaches. So there is the first one, which is kind of, I think, more direct, but the other one which seems also, the second approach we'll talk about will be more multi-purpose, but maybe is requires a bit more thought. But okay, so let's start again with our favorite example, which is Z2 synchronization. And you have again your matrix. Okay. So looking at this, you can say, well, my vector sigma I know is in, is a vector of length n with entries plus or minus 1, right? So if I had, infinite computational power, I would just look at the ML estimator, right? The MLE, which is, you can write this out, but one can show that this is nothing but the argmax of V transpose MV. Okay? So if I could do the optimization, if I could optimize over the hypercube, this is something that would be very reasonable. Okay? But this is not something that we can do in practice. So you can say, okay, I can try to come up with an alternative estimator that I get by a convex relaxation of this problem. Okay. So what do we do? So we say, okay, I'm basically looking at this problem where I'm trying to maximize V transpose MV subject to the constraint that Vi is in plus or minus 1. So this is equivalent to the following problem, where I maximize trace of MVV transpose subject to the constraint that Vi squared is equal to 1. So this is the usual semi-definite lifting for people in the audience who have seen this before. And then I can say, okay, this is equivalent to solving the following problem. Max over the trace of Mx subject to the constraint that x is positive semi-definite, xii is 1 for all I, and rank of x is equal to 1. Right? So what I did here essentially is to say, okay, I take this matrix, V outer product V. I write it in terms of some matrix X. Naturally, V outer product, this matrix is positive semi-definite. Its diagonal entries are exactly Vi square. So therefore, I put in the constraint that they need to be equal to 1. And then if I have the rank constraint, then X can always be decomposed as VV transpose. So these two problems are exactly equivalent. So far, I haven't done anything. I'm still solving MLE. Right? But you see that, okay, on the semi-definite cone, this is a linear objective function. And these are linear equalities. The only nonlinear constraint here essentially comes from the rank constraint. Right? So therefore, now you can look at this convex relaxation. Where you say that I will instead look at I just drop the rank constraint, right? So I look at max of trace Mx such that x is positive semi-definite, xii is 1, and that's it. Right? This is a convex problem. We know how to solve this. And once I get my x hat as dp, I will try to round it somehow and get some sigma hat from this. Right? I'll need some rounding procedure appropriate later. Right? But this would be a natural semi-definite programming based estimate for the underlying community structure, or the underlying spike in this case. Okay, questions? Okay, and then there is a similar algorithm that you can implement for community detection. Where you take your matrix A, which is your adjacency matrix, and then you look at the same problem. You maximize A minus D over N, 1, 1 transpose, and X, subject to the constraint that X is positive semi-definite, Xii is 1. Yeah. And then once you get the solution, you round it. So you get X hat SDP, and you round it to get some sigma hat. Okay, so what is known about these things? So the first analysis for this SDP in the context of the community detection problem actually goes back to a paper of Guedon and Vershinin. And then we had some result. Ours was in 2016. I think this was in 2015. But let me describe the results. There's something interesting here. So first, let's say let me state the result for Z2 sync. So let me call this star, and let me call this double star. So the result is that the SDP star allows detection and weak recovery as soon as lambda is bigger than 1. Okay. So again, a nice estimator, right? Lambda is equals 1 is the information theoretic threshold. As soon as you go beyond lambda equals 1, if you look at this SDP and if you look at its value, then based on this you can detect. And then if you have your solution, you can round it appropriately and get something that has some non-trivial correlation. Okay, so that's good. The result for community detection this is a bit more involved. So the idea is as follows. You fix any lambda which is 1 plus epsilon. Okay. Then there exists some d naught which is a function of epsilon such that if d is bigger than d naught, recall that d is again the average degree, then SDP double star performs detection and weak recovery for lambda bigger than 1 plus epsilon. I should just say here fix epsilon positive. Okay, so in words, what am I saying? So I'm saying that if you are above 1, which is the information theoretic threshold, depending on how far above this threshold, if your graph is dense enough, then SDP will work. That's what I'm saying. But this statement is not as clean as this particular statement, right? And you might say, okay, why is this, why do you need this? Actually, this turns out that this is necessary, so I'll talk about that in a bit. But any questions about just the statement? Yeah.
Are you going to tell us what kind of rounding you're going to do?
So I don't plan to talk about it in depth, but roughly the algorithm is that you have your x hat SDP. This is a positive semidefinite matrix. So then you draw a Gaussian matrix with this as your positive, this as your covariance. Mm-hmm. And then once you have that Gaussian, you round it.
What do you mean round? Because x is a matrix, sigma is a vector, right?
Yeah. So once you have the Gaussian vector, then you round its entries. Yeah.
Can extracting the largest eigenvector of x hat and
yeah, so that is one other natural rounding scheme, right? I think in our paper we worked with this Gaussian kind of sampling scheme. I think because I think that's more of a technical thing. I don't think we proved that just working with the top eigenvector of x hat works.
Can we do something like the max cut, random plan?
Yeah, essentially, the rounding that we were doing was of that flavor. So it's very much related. Yeah, this is the usual Gormans-Williamson SDP for max cut, right?
So can you think of these SDPs as to compare them to your spectral algorithm, that they are kind of looking for a direction which is more spread out, rather than...
Yeah, so this condition that xii is 1, this essentially kind of helps rule out rank 1 things which put most of the mass on high degree vertices. So that's why they guard against this thing that makes naive spectral algorithms go wrong, but otherwise they're kind of doing the same thing. They're still kind of looking for that direction. Okay, so why do I have this thing? So generally, if you fix the value of d, right? Fix some d which is greater than 1. Let's say you fix d to be 5 or something. Then you have your information theoretic threshold, which is 1. And in principle, you have the particular value of lambda at which the SDP starts to work. Right? By definition, lambda SDP is to the right of the information theoretic threshold. Right? That's the definition. But in fact, there is a result by Perry et al. So this is a result by Ankur Moitra and his students at MIT, Amelia Perry. I think Alex Wine was also on this paper. So they have this very interesting result that in fact, for a fixed value of d, the SDP does not attain the information theoretic threshold. Okay? So there is a gap. There is a real gap. Okay? And in fact, they prove that many classes of algorithms that are robust in a certain sense, they cannot attain this information theoretic threshold. What this result here is saying is that now if you make the degree grow, essentially this kind of shifts back to 1. And in fact, okay, if you do simulations, you see, okay, this goes to 1 fairly quickly. You don't need your degree to be super large. Degree 5 or 10 is already good enough. But at a fixed value of d, there is a gap here. Okay? So one needs to state this in this form, and you cannot really improve it, even if you work hard. Okay?
But that wasn't such an issue in the previous, like looking at the non-backtracking.
Yeah. So for the non-backtracking walk, it was good in the sense that it works as soon as lambda is bigger than 1. But it also crucially exploits like all characteristics in the model. So what is good about the SDP here is that the SDP essentially gives you a certain degree of robustness as well. So instead of observing the original graph, if you observe the graph with some small other planted things here and there, that doesn't really change the value of the SDP too much. It can affect spectral algorithms much more. So convex relaxation based methods are much more robust, but as a result, they are not exploiting sort of all the information present in the model. Now I think, okay, in practice one can argue if you should trust all your model characteristics, because okay, if whether your data actually comes from the model or not is always a question. But from a purely theoretical perspective, you do have this gap persisting. Okay.
So again, a follow-up question on this. So are there better SDPs more for which there is no gap? Or?
Okay. As far as I know, no. Yeah, I don't know. This is the best. But okay, I haven't been completely up to date on the more recent results. So there has been, of course, a lot of push in looking at higher levels of SOS hierarchy and things like that in this context. I know those results more in the context of the Z2 synchronization type model. I'm not sure if those methods can break this barrier. I think these algorithms would still have the same degree of robustness, so this same lower bound might still rule them out. But yeah, I would have to check. Okay. Okay, so some comments about these, right? Going back to sort of the spectral algorithms and sort of convex relaxation-based methods, I should say, and I tried to say a bit more about this in the homework problems for today. These results, I mean, the exact behavior of these algorithms, they actually depend on the density of the graph quite a lot. So for denser graphs, behavior is different. So for example, if you have a 2 community stochastic block model where Pn and Qn are bigger than, let's say, some polylogarithmic power 4 or something over n, in these cases, the spectrum actually behaves, even the naive spectral algorithm behaves quite well. And there are now very fine and precise results that are known. So naive spectral works well. And this is now very well understood. And even the behavior of the problem is quite different. So if you have much more edges, you can actually try to do more. So in fact, in these cases, sort of, once the degree is at least logarithmically growing, you can go beyond weak recovery. You can actually look for exact recovery possible in denser regimes. This you sort of expect in that, as we discussed yesterday, the main reason why we can't do exact recovery in the very sparse case is that there are isolated vertices. So if your graph becomes denser, at some point all the vertices become connected. So you would expect, that you can actually get some information about every vertex. So in particular, once the degree is logarithmic and higher, you can go for exact recovery. And people have studied, spectral algorithms, SDP-based algorithms for exact recovery in these more dense settings, and those are well known. Okay. So I tried to talk a bit about the SDP-based method for graphs with average logarithmic degree in the homework. Okay. Any questions? Okay. Actually, no. To go back to Mohit's question. I was wrong. There are other SDPs that will work. I will talk about them right now.
Intuitively, SDPs are always stronger than computing mathematical algorithms. So in some sense.
No, no. I wasn't thinking about the most relevant result, but I realize I will talk about it right now. So yes, there is a positive answer to this question. Okay. But okay, it's a slightly different perspective, and okay, let me talk about this. Okay, so right. So here is a second approach that kind of bypasses the issues that I mentioned. This is this meta approach due to Hopkins, so Sam Hopkins and David Steurer. Right, so they have this approach, which goes beyond the difficulties that I mentioned. And this seems to be, a meta strategy that works in many of these problems. So I think it's sort of super useful. So what is the meta algorithm? So the meta algorithm has two steps. The first step is to construct a low degree polynomial in the data entries to estimate, okay, in this context you're trying to estimate something like sigma outer product. But in other cases, if you can estimate like some tensor power of sigma, that's good. And then you apply a robust eigenvector or SDP-based algorithm to construct sigma hat from the prior estimate that we constructed in step 1. Okay? So that's kind of the meta strategy, but I'll talk more about it. So what is this idea? The idea here is that you get this data. Based on the data, you calculate some low degree polynomial in the entries of your data that is essentially trying to give you some estimate for sigma outer product in this case. And then once you have this noisy estimate for sigma outer product, you do some robust projection algorithm to actually construct sigma hat. Okay? So what I plan to do is to talk about the first step, because I think that's where sort of the problem-specific intuitions come in. The second step is sort of more a unified black box kind of strategy that Hopkins and Steurer implemented. So if you're interested, please look in their paper. I'll talk about the first step. In their paper, they already talk about applying this strategy in the context of community detection and a bunch of other problems. And in our work, we have found this strategy to be really useful, even in the context of this contextual block model that I introduced yesterday. Without this strategy, I don't quite know how else to go about in the contextual case. Okay. But first, let me talk about the application of this strategy just for the block model, right? Okay, so what is the idea? So application to community detection let me change the pen. Right, so I have, again, A, which is my adjacency matrix. Right. So essentially in their strategy, it turns out that, okay, I'm trying to construct a noisy estimate for this rank 1 matrix sigma sigma transpose, right? So if I look at the matrix sigma sigma transpose, its ijth entry is just sigma I sigma j. Right? So what I could try to do is to element-wise construct an estimate for sigma I sigma j. Okay, I can try to do that. So how do I do that? So let me just redefine two things. So D is A plus B on 2, and I'll define epsilon to be A minus B on A plus B. And you can see that epsilon squared D is sort of related to this parameter squared. Yeah, so it's related to it's A minus B squared on 2 times A plus B. So it's related to our parameter lambda that we've been using so far, right? So just to say that in this parameterization, detection and weak recovery possible if and only if epsilon squared D is bigger than 1. Right? Okay, so what can you do? I really like this approach. So they say, okay, look at this entry Aij minus D over n, and then look at n over epsilon D. This is just algebra. Look at this entry, Pij, right? You can construct this if I give you the adjacency matrix, right? And this is a low degree polynomial in the data. This is a linear polynomial. It's a polynomial of degree 1. And if you look at its expectation, then this turns out to be exactly sigma I sigma j. Okay, this you can calculate. Okay, so this by itself already is a polynomial estimate for sigma I sigma j. But this is not a very good estimate, right? This is not a very good estimate simply because if you calculate what is the variance of Pij, and let's say you look at the expected variance, this is roughly of order n over epsilon squared d. Okay? So epsilon squared d is a constant and n is very large, right? So this is a low degree estimate for sigma I, sigma j, but the variance is very large. So there's too much noise in this estimate and it doesn't really help. Okay, that's fine. But now, once you see this, you can try to boost your estimate. Okay, what can you do? You can say, fine, let's say I have I, let's say I have j. I want to get an estimate for sigma I, sigma j. I can construct a length 2 path which goes from I to k and k to j, right? And then if I call this path alpha, I can define P alpha of my adjacency matrix as essentially the product, or in this case just these two entries, right? Pij, Pik times Pkj. Okay, and if I calculate expectation of P alpha of A given sigma, this will just turn out to be sigma I, sigma k, and then sigma j. So this is still sigma I, sigma j. Okay. So in terms of expectation, it's good. And if I look at the expected variance of P alpha given sigma, then this is still of order, okay, this is growing actually. So this turns out to be n over epsilon squared d raised to the L, where L is the length of the path. Okay. Okay, so you might say, okay, what did I gain? I got like another low degree estimate, now something that is of degree 2. I still get an unbiased estimate, but my variance still seems to grow. But now you say, okay, I have like some combinatorial gain because I can play with what is the value of k. Right? I can choose different paths which all go from I to j via different intermediate points, and all of them give me estimates of sigma I and sigma j. Okay? And so I can then average all of these estimates and gain in terms of the variance, right? So if I average, then I have roughly n to the L minus 1 paths. And now if, okay, so there is a big if here, if all of these paths give me independent estimates, then in terms of my variance factor, this will go down to, once I average, this will go down to n over epsilon squared d raised to the L. Okay, but I'm making this assumption that every estimate, is independent. Okay, great. And so now you can sort of see where you would run with this, right? Once you have this intuition, you would say, fine. Therefore, if I am above the information theoretic threshold, so if epsilon squared d is some 1 plus delta, then there exists L which is of the form some small constant times log n, such that sigma I, sigma j hat is a consistent estimate. Right? Where I choose this constant little c depending on delta. And this is essentially the algorithm that you can actually make work. Okay, but you need to be a bit more careful here. You assume that you look at all these paths. By the way, I should remark here that I'm looking at paths over the complete graph, right? Not just paths on the graph. These are paths on the complete graph on n vertices. All of them give me some information. Along each edge, I just multiply aij minus d over n. If aij is 0, I get this factor negative d over n. If it's 1, I get this factor 1 minus d over n. That's what I get, right? Okay. So what about independence of the estimators? Right? If I choose too many paths, then the paths kind of start overlapping with each other. If they overlap, there's more and more dependence. Things can go wrong. And so you'll say, okay, one way to get independence is to consider less estimators. Then paths don't really interact as much. I have more independence. But if you don't take a lot of estimators, then you don't get this gain, this combinatorial gain that you were getting out of averaging. So it's a fight between sort of two different features. And what Hopkins and Steurer prove that choosing self-avoiding walks work. Right? So their estimate essentially at the end of the day is that you take any two vertices I and j, you look at all paths of length some c log n, between I and j that are self-avoiding. For each such path, you calculate these estimates just by multiplying these things along the edges. Average all these estimators. Whatever you get becomes the ijth entry of your matrix. And then you do some robust spectral or SDP-based algorithm. And they prove that this will give you weak recovery. Okay.
What is the complexity of this? Like, is it easy to?
Right. So they talk a lot about this. So if you are clever, you can do this in like quasi-polynomial time and stuff. But this is still like, okay, this is not like a polynomial time thing, but it's not exponential time. And there are special tricks that you can do to kind of make them more efficient and stuff. But that's very special to this algorithm. But generally, counting these self-avoiding walks is difficult.
And are these self-avoiding walks of the order of n power n minus 1?
Yeah, so the main thing is that you establish that if you only look at self-avoiding walks, then in terms of the combinatorial factor, you're still getting n to the L minus 1 walks. So you don't lose too much. And so this is another sort of intuition, right? That at the end of the day, if you're estimating sigma I, sigma j, what you're trying to say is, all I want is for every pair of vertices, I want to know if they are in the same group or not. That's what sigma I, sigma j is telling me, right? And so if I average this information that I get from all these paths of long length, then I get a lot of information, I boost them. The entire question is, okay, do I have enough independent information? And self-avoiding walks give you that. Okay. Any questions so far?
So these self-avoiding walk are you doing on the complete graph?
On the complete graph. On the complete graph. Not on the observed graph. Yeah.
So just to be clear, they don't show that the self-avoiding walks are independent, but they take care of the correlation.
They take care of the correlation. They show that the correlation isn't large enough. Yeah, the correlation among the estimates doesn't really make things go haywire. Okay, so I have been influenced quite a lot with this general strategy, and I think it has been really helpful because it's kind of like really a meta strategy that you can implement for many different problems. So I want to talk briefly, maybe for 10-ish minutes, about how one can go about applying this same strategy in the context of the contextual block model, right?
Sorry if I missed this. At this level, so how is this, what advantages does this have over, let's say, the Masoli methods for community detection?
Not much. If you only care about the community detection problem, then it's giving you the same result.
In worse time, right?
In worse time. But the general strategy seems to be much more widely applicable. So for example, in the next example that I'll tell you about, I don't know what is the analog of the non-backtracking matrix, right? Or at least I can't prove anything about it. But if I follow this meta strategy, I can still prove something. Okay? So it seems to be a bit more widely applicable. And even in their original work, Hopkins and Storer, they make this point. They apply it to a wide variety of other examples. This is just one of their motivations. So, okay, so let's recall the contextual block model. The contextual block model. So here my setting was that I have this graph that's sampled from a stochastic block model, usual two communities, edge probabilities A over n, B over n. Okay? And in addition, at each node, I observe a vector of covariates bi, which is p-dimensional. And we were sampling this bi to be like square root mu over n, sigma I times u, plus zi over square root p, right? Where u was some unknown latent cluster center. So this was like Gaussian mixtures, and zi was normal zero identity. This was the additive noise. Everything was independent. Right? This was our model. And the question essentially was, okay, how to combine graph with covariates to do community detection. Right? And our result essentially was that, let me just look at my scaling. Yeah, so I worked under sort of this high dimensional scaling, so p by n converges to some constant 1 over gamma. And then the theorem is that the threshold for detection and weak recovery is lambda squared plus mu squared on gamma bigger than 1. Right? Okay, so how do I get this threshold, right? So here is the idea. So I plan to sort of use the same meta strategy as Hopkins and Storer, right? So I need to construct, again, this matrix that is a low degree polynomial estimate for sigma I, sigma j. And then I can do whatever decomposition I need to do. How do I construct this estimate in this problem and combine information across sources, right? That's sort of interesting. So the idea here is as follows. I construct here the so-called factor graph for this problem. So these represent my vertices in the graph. There are n of them. Okay? And on this side, I construct an additional set of p vertices, which correspond to the p covariates that I observe. Right? So each bi is p-dimensional. So I have p features. And so I'll number them, let's say, from 1 prime to p prime. Right? I have two sets of vertices. Now, what I do here is that, remember this element Pij A that we constructed last time. This was like n over epsilon d times Aij minus d over n, right? So what I will do here is that I will construct a weighted complete graph on these n nodes, and the weight for each edge here is basically this Pij, right? That's what I'll do. Turns out if I just look at these Bi, the covariate vectors, if I go from, let's say if this is I and this is j, if I go from I to j via one of these wedge paths, then I also get an independent bit of information regarding sigma I, sigma j by doing a similar strategy just with this, right? So I have, for each such A here, I have some estimate or some low degree polynomial. Let's say I call this Pija, right, of B. That's a different bit of information. And so naturally what I can now do is that when I have to count paths from I to j, I can construct paths on this larger augmented graph that has the complete graph on one side and the complete weighted bipartite graph on this side, right? And I construct paths on this larger graph, right? And each such path now gives me some information about sigma I, sigma j, and you can see clearly I have more information, right? I have more paths here. Okay. Now the interesting question here, and this was what really it was illuminating when we worked through this strategy, because there is this question that like, okay, how should I, what kind of contributions should I look at in terms of edges, right? I can have edges on the complete graph here, I can have edges on the complete bipartite graph, and I can have different mixtures of these two kinds of edges, right? How should I combine them? I can maybe just restrict myself to edges on the complete graph, right? Of course you expect that to not work, right? Because if you are in a regime where this is bigger than 1 but lambda itself is less than 1, then if I just take edges from this side, they will be too noisy. They don't work, right? So it turns out that if you maximize the SNR that you get by varying the proportions of the two types of edges, turns out that the optimal fraction is to take them in the ratio lambda squared to mu squared on gamma. This is the optimal fraction in which you should take these two kinds of edges, and if you do this, then you will exactly recover this threshold. And then you do the same strategy. So you consider self-avoiding walks of length some c log n, but now you consider them in a way so that they have these two kinds of edges in the proportion lambda squared to mu squared on gamma. And once you do this, then you follow the same meta strategy. Once you have the estimate for sigma sigma transpose, you do the projection, you will get your estimates. Okay, you can do weak recovery based on this. So this was sort of what we did. This was actually in a recent paper with Chen Lu, now in 2020. But I really like this in the sense that before I really learned about this meta strategy, I did not have any other algorithm that works in this contextual block model setting up to this conjectured threshold for any average degree bigger than 1. But I think there is a lot more to be done here. I plan to talk more about it on Friday in terms of, I think, what more can be done. But okay, let me stop here. Let me know if there are any questions. The plan for the next lecture is to kind of go beyond this in the sense that our entire lecture today was based on weak recovery and getting algorithms that perform weak recovery. You could go beyond this and you can say, okay, can I recover my signals in an optimal sense? So we'll make that precise, and we'll talk about some actually non-convex optimization methods that can also be useful for these problems. Those are, I think, the investigations into these algorithms, I think, is more recent and more ongoing. So I think there's a lot to be done in that sphere, and that's what we'll talk about on Thursday.